Hello, this is A Squared at mathandstuff.com. Today we'll sing a derivative. We'll take a derivative or two or three by singing rather than symbol speaking. If you go to the whole home page and scroll down to the bottom, there's a link for mathandstuff.com and video. If you were to take that link, it would bring you to a page which lists the videos already prepared, and I would not bother with this table of contents. I would scroll down because I've grouped the videos here by topic rather than just by broad topic. Dictionary, pre-calculus, calculus. We're going to use calculus. There are others. I'm not going through that. We're taking a derivative by singing. This is take a derivative by singing. This is the perspective we're using. Most of the time, when derivative notation is written, it's either written in symbols, or that's almost always the way it's written, or it's spoken in formal mathematics. Instead, we're using the mother tongue. In other words, common, everyday, for me, English, because that's the most sophisticated and also the least sophisticated way of presenting. There are other videos on other ways. This is not a normal calc version. We'll look at that in a moment. This book I'm showing you here is a cover page of the textbook. It's an open resource book that I'm currently using now when I teach calculus by department decision. This is how the author of the book I'm using presents the product, quotient, and chain rule. It's a traditional perspective. His words are, let f and g be differentiable functions on an opened interval I, then fg is a differentiable function on I. That's correct mathematics. And he's positioned his terms in an order that I don't prefer. By commutativity of multiplication and addition, I'm going to soon sing it the way I prefer it, so it parallels the quotient rule as much as possible. So the songs will be similar. Now he calls it let f and g be differentiable functions. And I'm going to read to you, then fg is a differentiable function. It really says this is what the words are that match the symbols. The derivative of the product of functions f and g is the derivative of f times g plus the derivative of g times f. You start to hear the song I'm about to sing. I would say the derivative of the first times the second plus the derivative of the second times the first. Now, listen to how similar the quotient rule is. The derivative of the first times the second minus the derivative of the second times the first, all over the second squared. And when he presents that, he points out the fact that it's a messy symbolism. So he tries to make it better. And his perspective is very high symbolic. So that's the route he can go with. And that's the best he can do, given it's a textbook. Because I can communicate orally where he cannot. He can only do it on paper, and his background is symbols. My background is teaching to an audience that's more accustomed to spoken words. Here's his chain rule. The derivative of the composite of a function is the derivative of the outer function evaluated at the inner times the derivative of the inner. We're not going to use his, we're going to use our version. All this is downloadable and linked at the site I stated. Here's the product of two functions. The derivative of the product is the derivative of the first times the second plus the derivative of the second times the first. All in English, no symbol speak. The quotient, the derivative of the first times the second minus the derivative of the second times the first, all over the second squared. For the chain rule, the derivative of the outside evaluated at the inside times the derivative of the inside. We're ready to take a derivative by singing. Exactly the same content as the typical calculus text, but slightly different presentation. The derivative of the first times the second plus the derivative of the second times the first. Or the quotient, the derivative of the first times the second minus the derivative of the second times the first, all over the second squared. For the chain rule, the derivative of the outer evaluated at the inner times the derivative of the inner. Three problems. We're going to do one of each kind. Here's the product, here's a quotient, and here's a composition. Let's sing the derivative. The derivative of the first times the second plus the derivative of the second times the first. Done. Of course, you could expand it and do it that way, but just an example. Quotient, the tangent may not look like a quotient. You have to remember your trig identities. It's the sine divided by the cosine. That makes the derivative one we can sing. The derivative of the first times the second minus the derivative of the second times the first. All over the second squared. Planing it, simplifying it, the opposite of a negative is positive, makes this sine squared. And I'm writing it in this form because I think my students will recognize it as a Pythagorean identity. more easily with the sign first. And that's a 1. Reciprocal of the cosine is the secant. And that's the derivative. Now, this is a chain rule. The outer function is a cube. I find it easier to write it so you can see what the outer and inner are. But still just a song. The derivative of the outer evaluated at the inner times the derivative of the inner. Done. Seeing a derivative. We've done the easy ones. Now let's do the longer chain rule. The longer chain rule. The derivative of, let's make it even bigger. The derivative of the outer evaluated at the inner. That's the regular song that you remember. So it's the derivative of the outer evaluated at the inner times the derivative of the inner is how one normally sings it. We're now going to sing it. The derivative of the outer evaluated at the inner times the derivative of that inner times the derivative of that inner times the derivative of that inner for as long as it takes. I've listed the problems in a level of sophistication or difficulty. We're doing 3 problems. The first one, the innermost is just a variable, not even a function, but you're taking the sign of that and you're cubing it. So it's the sine cubed of x. Then making it more sophisticated, the x, instead of being a variable, becomes the function 4x. And even more sophisticated, instead of the function 4x, it becomes the natural log of 4x. But all you have to do is sing it. The derivative is the derivative of the outer evaluated at the inner times the derivative of the inner. Next, the derivative is the derivative of the outer evaluated at the inner times the derivative of the inner times the derivative of the new inner. That's the new inner. Done. I'm not even going to simplify it. The derivative is the derivative of the outer evaluated at the inner times the derivative of the inner times the derivative of the new inner times the derivative of the new inner. The hard part is not taking the derivative. The hard part is cleaning up the algebra afterwards. So at this point in time, you've learned 4 songs. You've learned 4 songs. The derivative of the first times the second plus the derivative of the second times the first, or the quotient. The derivative of the first times the second minus the derivative of the second times the first, all over the second squared. For the composite function, the derivative of the outer evaluated at the inner times the derivative of the inner. And for a longer chain rule, the derivative of the outer evaluated at the inner times the derivative of that inner times the derivative of that inner, and so on.